Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thanks again to our Patreon subscribers.
For less than the cost of almost anything, because inflation sucks, you can hear us talk about more interesting engineering failures. How much does that cost per month, Nicole?
$5 Canadian per month to get more interesting engineering failure episodes. And I wanted to add that we have on our website, failurology.ca, if you go to the exclusive content page, there's a list of all of the mini failures that we've done so far. So you can go there and see if there's any that interest you or some that you want to listen to. And then you kind of know what you're getting yourself into on our Patreon instead of just going in blind. So we do publish that list there, and it gets regularly updated.
There's some great mini failures too. I was just thinking there's a beer flood on there. There's the molasses floods. There's some airplane related ones. There's some train ones. There's some amusement park ones. There's something on there for everyone.
Some fire ones too. Those are good. Yeah. So on this episode of Failurology, we have a guest. We're joined by Leanne, a mechanical engineer in the renewables industry. Welcome, Leanne. Thanks for joining us.
Hey, thanks for having me. I've been working in the waste to energy side of the renewables industry for about 15 years. And I've done a little bit of everything from process design to plant commissioning. And I've spent the last 6 years doing maintenance and reliability at a chemical plant. And we're converting municipal waste into methanol. When I was in my undergrad, I actually got to do a student exchange in Germany for a summer where I learned about all the different renewable technologies that they're using at the time. And I'm very excited to talk with you guys about turbines today. So thanks for having me again.
We're so excited to have you on Failurology. This is something that I don't know a lot about. I've seen wind turbines, but I've never thought about the failures or the engineering that goes behind them. So it's great that you were able to join us.
Yeah, so one thing that's interesting about wind turbine failures is, especially the ones we're going to talk about, is they're very visible. So wind turbines are kind of out in the open and you can see them, and when they fail, it can be very spectacular. A very interesting show.
Spectacular is a great word.
I've seen a couple YouTube videos of failures, and they're fairly catastrophic failures when they do fail. And where Nicole and I live, just to the south of Calgary, down by Pincher Creek, it's quite windy there. So there are some wind turbines, and they do power, and we'll talk about this a little bit later on, they do power part of our transportation system here in Calgary, which I think is really cool.
It's a great alternative form of energy. You know, in Alberta, we get a lot of pro-oil and gas voices, and I support those voices, but I do think that diversification is good in any market, because then when the bottom falls out of the bucket, you've got other avenues that you have already prepared to take you forward. And so I think, you know, having a little bit of everything in our energy portfolio is a fantastic idea.
Oh, yeah.
Yeah, absolutely. And I think we're seeing, some typical, standard oil and gas companies or companies that had a lot of oil and gas portfolio related things, that they are branching out into renewable energy resources, which I think is a great thing to see.
Yeah, what I was going to say is not a free, well, it is a free resource. It's just blowing around out there, and it's something that's never going away. So it's good that we can harness that into electricity.
Yeah, especially in southern Alberta, I've done some projects down just around Lethbridge. You have to get special roofing material because the wind ratings have to meet a certain level because it's so windy down there. And I've heard a lot of people that live there also have, they live there and they love it, but they struggle with the wind because it blows so hard sometimes. And so I think wind turbines are a great application for that area.
Mm-hmm. And you've noticed that all the trees in Lethbridge are kind of leaning to one side?
I didn't notice that. The windmills are also really pretty because when you're driving down to Lethbridge, if you're driving south, so to your right, which is looking west, you see all these wind turbines, but you're kind of still in the prairie. So you've got all this prairie grass, you've got the wind turbines, and then you've got the mountains in the background. So it just looks really pretty as someone who didn't grow up in Alberta driving down there for the first time. I just thought that visual was really cool.
This week in engineering news, staying on the theme of this episode, boosting wind farm output without new equipment. This one, like a lot of our news items, comes from MIT. Wind farms around the world, they produce more than 5% of the world's electricity. Each wind turbine in the farm is controlled as an individual freestanding unit, even when there are dozens or hundreds of turbines in the farm. Engineers at MIT, the smart people that they are, found that just by modeling the wind flow of the entire farm, they can optimize individual units within the farm. The increase in energy output is modeled at about 1.2% overall and 3% for optimal wind speeds. If this algorithm was implemented at every wind farm in the world, it would be the same as adding 3,600 new wind turbines, or enough to power 3 million homes. So this is not an insignificant increase.
So in order to get the most out of wind farm areas, the land is expensive. The turbines are spaced close together, which means that turbines in the front of the wind farm send turbulent wakes to those downwind, which is something that the current method of controlling turbines individually does not take into account. And I have to admit, when I read this article, this seems pretty straightforward as someone who doesn't work in this area. This is not my area of expertise, wind turbines. I've never worked on one. But having the wind farm work as a cohesive unit does make sense. I feel bad for saying, why didn't you guys figure this out sooner? But this does seem pretty straightforward. It does seem a little silly to have them all controlled individually. I think you are going to be able to address some of that turbulent wake controlling them individually, because at least you're still making adjustments, but you're not treating them as a single unit, even though they impact each other. So the algorithm that they developed uses physics-based data-assisted modeling that learns from operational wind farm data to find the optimal orientation for each turbine at a given time, depending on the wind conditions. And then the turbines adjust their vertical axis position to align the incoming wind direction and speed. The article is quite informative, and it includes a lot more information about how they developed and tested the algorithm in real wind farms around the world. So if you want to read more about it, check out the link on the webpage for this episode at failureology.ca.
This week's episode of Failureology is brought to you by the Sit Down Stand Up Paddleboard Company.
Whether you like to sit down or stand up,
the Sit Down Stand Up Paddleboard Company has something for you.
Don't miss our paddle sale. It's quite the ordeal. Now on to this week's engineering failure, wind turbines. We're going to do something a little different on today's episode. We normally would pick one failure or maybe two similar failures. I know we've done floating bridges. We put two of those together in one episode. But the wind turbine failures, there's a lot of them, and they're all pretty straightforward. I think if we were to do them all, it would be kind of a weird episode, or maybe a bunch of mini failure episodes, and we didn't want to do that. So what we're going to do today instead, something different, something we haven't done before, we're going to talk about all of the different ways in which a wind turbine can fail, and then discuss some examples of each of those types. And we've broken it down into 4 different kinds of failures. But before we get into that, let's talk about, we've kind of touched a little bit on wind farm impact in Alberta, but Brian, do you want to tell us a little bit more? You mentioned the sea train being wind powered, which I think is pretty cool. Do you want us to tell us a little bit more about that?
Yeah, so for listeners that don't know a lot about Calgary, Alberta, it's really the Houston of Canada is probably a good way to describe it. So a lot of oil and gas companies have their head offices here in Calgary. So as Nicole mentioned, oil and gas is a big contributor to the revenue for Calgary. There's tons of companies that are directly or indirectly related to oil and gas servicing, so extraction of oil and gas out of the ground, or the processing or the refining of oil and gas. And one of the things that they've done in Calgary here is our light rail transportation system that's known as the Sea Train. It's 100% powered by renewable energy, which is the only light rail transportation system in North America that is powered by renewable energy. And the way that they do this is there isn't a dedicated wind farm that's dedicated solely to the Sea Train system, but what the transportation or the transit authority has done is they've purchased the equivalent amount of energy from a wind farm located near Calgary. So the city purchases essentially enough wind power to match the LRT usage, which makes it, I guess, 100% funded by renewable energy, which I still think is a really cool thing in a city that's predominantly known for oil and gas and the Calgary Stampede and possibly the 1988 Winter Olympics.
Possibly. Probably a little bit less that one. It's been a while.
Some of us are very old and remember them very fondly.
I think the other thing that's interesting about Calgary that not a lot of people know, and we're not talking about solar today, but along the vein of renewables, Calgary gets definitely over 300 days of sunshine a year. I think we're usually around the 330-day mark. We're the sunniest large major city in Canada. There's a lot of opportunities for solar here as well. We also have a lot of land and a lot of really smart people. So we have a lot of people with the skill set to take on these different renewable projects, which I think is really interesting. I also think there's a way to use air generated by moving trains, specifically in a tunnel, as an energy source. This is just something that I was thinking about as I was researching this episode. I don't know how viable it would be and if you get the most bang for your buck, but I think, somewhere like New York City, an underground tunnel system with a lot of trains that are running all the time, I think could potentially benefit from something like that. So it's an interesting idea, full of ideas.
The high-speed train that they're proposing between Edmonton and Calgary, isn't that one going to be in a tunnel? I thought I heard that it's going to be a pressurized, like ultra high speed.
I've seen a number of proposals. Some of them are more viable than others. I feel that the tunnel option there, if you had unlimited funding, that one might be a good way to go. But I just can't see it being economically feasible to make it work. That would be a 300-kilometer long tunnel or 250-kilometer long tunnel. So I can't quite see it happening. I really hope it does happen because that would be really cool. But I think it would probably ultimately be cost prohibitive.
Yeah, because I think it's a new technology for trains, for high-speed maglev trains to be in a pressurized tunnel like that. But I feel like the route between Edmonton and Calgary would be like an ideal test area.
It's fairly flat. I mean, there's no mountains in the way. There's a number of fairly major river crossings. The elevation change is about 1,500 feet between Calgary and Edmonton. So Calgary's about 4,000 feet, and then Edmonton's at about 2,200 feet. So yeah, I think that's fairly flat as far as a grade goes over 250 kilometers. So yeah, I think that would be an ideal test area for a long train like that. Versus somewhere over in Sweden or Germany or somewhere where there's quite a few more mountains throughout the whole country.
That and population, like there's no cities, there's no population between. I mean, there is, but it's not like in Europe, like you're saying. You don't have to go around towns.
You'd really just have to stop in Red Deer and you'd be done.
Yeah.
The nice thing about the train from Calgary to Edmonton is, to me, that's step one. So you put the train in between Calgary to Edmonton, you have a stop in Red Deer. But then once you've got that infrastructure and you've proven, hopefully, that people will ride it and that it's a viable market, then you can start expanding that train. And so then it becomes much easier to get a train to Lethbridge and another one to Fort McMurray and one to Banff. And it seems way more doable to expand our network. Because when you look at Alberta as a province as a whole, it's a lot of train to connect all of the large cities. But when if you think, oh, I'm just going to start with these two and then go from there, I think that's a better way to go about it. And that's kind of how the C train in Calgary was approached. They built it, well, the initial one was a big push because they built it for the 88 Olympics, but then they've just been slowly adding stations and expanding the network from there.
Still don't have a train to the airport though.
Yeah, I know. It's embarrassing. We're one of the only major cities in North America that doesn't have a train at their airport. There are others. We're not the only one, but we're one of the only ones. But I think, our transportation is still significantly better than other cities. I've heard I don't even think Ottawa has a train network, which is pretty bad. The other thing that would be nice about connecting us to Edmonton is then we could get on via rail, because Calgary is not part of Canada's rail network. So if we wanted to take the train to Vancouver or Toronto, we'd have to drive to Edmonton first. And at that point, why not just fly or drive wherever we need to go? And so having the high-speed train to Edmonton would allow us to then jump onto that via rail network, which I think would also be beneficial. Not that I necessarily want to take a train to Ontario because it's a bit of a journey, but just the idea is nice to think about. I feel like we're left out of the train network. It sucks.
I think one of the issues that trains will always struggle with here in North America is that a lot of the rail rights and the right-of-way agreements are for companies that typically haul freight. So, CP Rail or CN Rail or BNSF or Union Pacific in the States, and passenger rail service really, kind of is a second priority or third priority to getting freight rail traffic through. So a lot of the passenger trains do wind up sitting for extended periods on various sidings.
Yeah, that's a great point. If we had more riders, that could shift, right? Like just because that's the way it is now doesn't mean that's the way it's going to be forever. And it might be that way forever, but
I don't see that shifting from the freight rail standpoint. Like they've had some of these right of way agreements and track in place for 100 plus years, and we've seen this in major cities. I mean, Calgary's a good example where the train does run right through the middle of downtown, and there is literally no incentive for the rail company to move those rails from downtown. I mean, it's cost prohibitive into the billions of dollars. I believe Edmonton moved their rail traffic from downtown to the north end of the city, and it was over $1 billion, I think, is what they wound up paying to the city of Edmonton, paying the rail company to move their lines and their yards outside of the city. So I hope the passenger stuff goes ahead. I just don't know if it's a viable thing to go ahead, unfortunately.
yeah, fair enough.
Oh, that was a long tangent.
We love trains. Leanne, what's the wind farm impact like in Germany?
Yeah, so in Germany, they're actually the largest wind power producer in the European Union by quite a large margin. They have over 64,000 megawatts installed wind turbines. And in 2020, which was their best year producing on record, they produced 132 terawatt hours of wind power, which is quite a lot. It turns out 20% of the electricity produced in all of Germany last year was wind power, which is compared to 6% in Alberta, for example. But overall, Germany was producing more wind power last year than all of Alberta's electricity generators combined. So just to give you a comparison, the land area mass, Germany is I think not quite 50% of the land mass of Alberta. I think it's that way. It's not the other way. In any case, I think what it means is a place like Alberta has a lot of potential for wind. There's so much land in Alberta, and especially in the southern parts where there's no trees and there's a little bit more population. So
Germany would also have a lot more people.
oh yeah, there's something like 80 million people here.
That's more than all of Canada.
That's more than Canada has.
We have about 4.5 million people in Alberta, so we have a lot of space.
Yeah. A lot of space and maybe not a lot of users, but I think in Alberta they're importing power some of the time. So they have a tie-in between BC to Saskatchewan, also to Montana. So they, instead of importing power from the local neighboring areas, I think there's potential to produce it locally, because we don't have a lot of potential for hydroelectricity, for example, as a renewable source.
We do have a lot of rivers, but not enough to kind of create hydro in the way that BC and Ontario and Quebec can.
Yeah, exactly. That's where BC gets a lot of their power from is hydro. So Germany is producing 20% of their overall electricity is coming from wind, but it took the last 14 years of product development and industry development and government initiative and really growing pains for wind power to climb that high. So from 6% where Alberta is today to 20% where Germany is now, it took 14 years for Germany to do it. But really in that span of time, the cost of wind power has been reduced by half. So it should be easier. There's a lot of experience and there's some better designs out there. So
yeah, that's the thing. That's the interesting thing about these other forms of energy generation is that as more people start to use them, they start to get better and more cost effective and more efficient because everyone is looking for a way to optimize that energy source and get the most out of it. And so we're seeing a lot of development over these different, solar is the same way. We're seeing a lot of improvements in solar energy as well as wind. So I think that's really cool. They kind of, I wouldn't say they sat fully stagnant, but they kind of plateaued, I think, for a while. And now we're starting to see another big push. Also, Europe is probably in a different position than North America with all of the things going on with Russia and trying to reduce that dependency. There's a bigger push and a lot more people are invested in making that change to get off of that dependency and to be able to to power their energy loads more independently. So I think that's also a driving factor. That's obviously a newer factor. That's over the last 6 months or a year, but it sounds like Germany was prepared. If anyone's going to innovate something, it's the Germans. They're pretty good at that stuff.
Yeah. Yeah.
After all of this positive discussion about wind turbines and renewable energy sources, we're going to move on to the failure portion of this episode. And like Nicole mentioned, there's 4 kind of broad categories that we found when we were researching this for failures of wind turbines. So I'll just kind of go over them at a very high level, and then we'll talk about a specific failure of each type, or a couple different specific failures of each type. So 4 types of wind turbine failure that we found were blade failure, generator failure, gearbox failure, and then the tower foundation failure, which to me, not being an expert in wind turbines, sounds like all of the parts of a wind turbine.
Pretty much.
Yeah. Yeah.
Failure number 1 for blade failures. So the main function of the blades, I'm sure most of you kind of know this, you can guess this, is the blades are there to boost energy production. Without the blades, you can't really generate any power because there'd be nothing for the wind to push on, nothing for it to turn. The way that power is increased, so you can either increase the length of the rotor blades on the wind turbine to catch more wind, or you can adjust the pitch angle of the blade to account for variable wind speeds or variable wind directions. And in 2001, the largest operating turbine was 14 megawatts with 107 meter long blades. Just to put that into perspective, when you're driving your car, 100 meters doesn't seem like a very long distance to drive. The odometer clicks over pretty quick. That's the length of a football field. So there's a blade, one blade, a single blade on the wind turbine is the length of a football field. To me, that is quite staggering, that something that's spinning in the air is the length of a football field. Like that's astounding. And I've watched some videos of the blades being transported, and the coordination that's required to drive these wind turbines to site on trucks is absolutely mind-blowing to me. How all of that works, because wind turbines, they're usually in fairly windy areas, they're on top of ridges, so the roads are not straight. They're not, an 8-lane interstate where they can block off a bunch of lanes. They're pretty narrow, windy roads, and somehow they maneuver these super long blades all the way to the top of these ridge lines. I'm impressed by that part, and just by the length of the blades. Unfortunately, though, with the length of the blades, longer blades, they do add additional stress along the entire length of the blade, just from the sheer weight of the blade, and also the momentum of the blade spinning through the air. So the adjustable blade portion as well, so being able to change the pitch of the blade, kind of the same way that you change the blade angle on a propeller in an airplane, there's a big mechanism that controls all of that blade angle. So again, this just adds to complexity, just an additional complexity issue that, again, can fail on the blade component there. So considering factors like wind magnitude, temperature, density, contamination, all of these things, they all vary wildly through the year, even hour by hour. Where I'm sure some of you live, the weather changes hour by hour, minute by minute. And the blades, they take the brunt force of all these changes. In 2018, it was estimated that 3,800 blades are damaged each year on some 700,000 installed blades. And the damage to this, it can be anywhere from cracking in the blade, in the gel coatings, to complete and unfortunately rapid destruction of these blades.
The blade failure is the most common failure of wind turbines, and that's not really surprising. These are the largest component at over 100 meters long, and they are exposed to a lot of things that I hadn't really considered, like rain and hail and freeze-thaw conditions and birds and all of those things. So there's a number of common failures or flaws that we see with wind turbine blades. Before I get into that list, I do want to mention that these blades are almost always made out of fiberglass. That's because of the lightweight and strong nature of fiberglass. And so it does allow you to get blades of that size. I think if they were trying to use a different material that was heavier, they wouldn't be able to go nearly as long. There'd be too much stress on the gearbox and the foundation. The common flaws of blade failure are debonding of the fiberglass layers, so those layers start to come apart. Joint failure at the blade root, so where the blade attaches to the turbine itself. Splitting of the blade along the fibers, so again, that's kind of goes part and parcel with debonding of the layers. Gel coat cracks, which allow for moisture ingress, so as these blades get hit with hail and birds and everything else, that exterior coating on the blades can start to wear away, and then as that happens, moisture can get inside the blade and start to damage it erosion at the leading edge, and that's the leading edge is the furthest, the tip of the blade, the furthest point from the foundation or from the turbine itself. Excessive blade flex, resulting in the blade striking the tower, or extreme load buckling, where the blade folds back in on itself, which would be really kind of scary to see. So because these are fiberglass, they do have a lot of give to them, which is another benefit of using fiberglass as the blade material. But because these blades are exposed to such extreme weather conditions in some circumstances, there's a lot of flex that gets put on that blade that can stress it and make it move and bend in all sorts of different ways. There's also the momentum of the blade going around that's also impacts that force. A number of the contributing factors that are leading to all of these different failures are weather. So I mentioned rain, hail, also ice, high wind, but even lightning strikes is another factor. Material or controls or braking failures can also lead to failure of the turbine blades. And then poor design that doesn't account for high wind conditions or fatigue design. So these wind turbines are sitting out in the wind all year round, 24/7, 365. And ideally they're spinning that whole time, but not necessarily. And you don't have control over the wind conditions. And so if the designers aren't looking at what the worst possible conditions can be and not planning for those, then you can see early failure of some of these blades from either high wind or just stress from fatigue.
Yeah, just talking about fatigue design, have you guys seen videos floating around? There's a pretty sizable research facility in Denmark, and they're doing wind turbine blade testing. And you can watch it, and they've got this kind of mass that's attached to the middle of the blade, and it's got a weight that's rotating around, and the blade is just flexing, and they're looking for the fatigue properties of those blades. It's really, really interesting to see them testing it and see how much research goes into the blade design.
I think I did see that video on Reddit. I think either the engineering subreddit or engineering porn is another good one. Weird name, but it's got good stuff. It's got the nerdiest of nerdy engineering stuff. But yeah, weird name.
Maybe don't look that one up at work. Like, I realize the content is probably all right for work, but depending what your IT administrators kind of has some settings set to, maybe just do that one at home.
Okay, so we can talk about a few examples of blade failures. First one is Perkins High School, which is located in Sandusky, Ohio, which is on the southern shore of Lake Erie. They had 3 20-kilowatt turbines installed January 3rd, 2009, and they were connected to the power grid on February 4th. A few days later, on February 7th, the weather was reasonably windy with 35 to 40 kilometer per hour winds, gusting up to 85 kilometers per hour. And I just wanted to note that the typical cutout speed for wind turbine is 25 meter per second wind speed, which is 90 kilometers an hour. And at that point, the controls basically turn the blade pitch to a position that stops the wind turbine, and it doesn't spin in wind speeds that are faster than 90 kilometers an hour. So the wind speed on average was 35 to 40 kilometers an hour and gusting up to 85. We weren't able to find any official reports, but the pre-investigation speculation was that one of the blades had flexed in a gust of wind and contacted the tower. The rotor then became unbalanced with only 2 out of 3 blades spinning, and the other 2 blades contacted the tower shortly afterwards. To make matters worse, at Perkins High School, a second failure occurred in that installation 2 years later, on November 29th, 2010. Again, we didn't find any official investigations for that failure, but there were rumors of sheared bolts at the connection of the root of the blade. In this instance, the turbine was brought to a stop before the other 2 blades had failed. It was reported that this was the 3rd set of blades that had been installed on the turbines. Presumably, both of the previous blade swap activities were done proactively as a result of the 2009, the first failure. Both of these failures fall into the what we call the infant mortality range of the reliability curve, and were likely either design error or could be maintenance error. In the first case, either the blades were too flexible, or could have been maybe the control system wasn't well tuned to handle gust of wind. Could have been the first time the machine had been turned on, and maybe it was a badly executed startup sequence. In the second case of the sheared bolts, could have been either design error or maintenance error. Maybe the wrong size of bolt or bolt grade or torque. The bolt torque could have been specified for the new and reinforced blades, or maybe just the wrong type of bolts were installed or improperly torqued.
We did find a similar bolt shear failure that occurred in Sedinge, Denmark on February 23rd, 2008, where the root cause of the sheared bolts was deemed to be insufficient bolt torque that allowed some of the bolts to fail in fatigue, which caused a domino effect for the remaining bolts. It is possible that the bolts had been insufficiently torqued since the turbine was installed in 2000, and the deficiency was not found in any of the annual inspections. Following the incident, it was recommended that the Danish wind turbine certifying body produce a guideline for ongoing service and maintenance of wind turbines in Denmark, including such critical items as bolt torque specifications and checks. Just as an aside, this is sort of related to bolt torque. At one point, many years ago, I was driving back from a hike, and one of the wheels on my car at the time, it decided that it no longer wanted to be part of the car. So I got to watch my front left tire bounce down the road in front of me as the car slowed down. So again, I don't know if that was related to bolt torque. I assume the car that I had, it was a Volvo. So instead of using a nut, it uses a full bolt. There's a big threaded bolt on there. So it was driving down a gravel road. So I don't know if they were improperly torqued at some point and they just started vibrating loose. But now, pretty much at every hike that I go on, or at least a hike where I have to go down a gravel road, I hop out and I check all of the torque on the bolts on the wheels. So yeah, it's important to have your bolts torqued properly. Nothing really resulted out of this incident. I went up and get a new tire. It cracked the hub on the wheel, so I got new tires, and that was about it. The car still runs. It got up to 400,000 kilometers, but check the torque on your wheels. It's important.
Yeah, I want to add, I've heard that story a number of times. Very funny story. But I want to add that road, if you're from Alberta, it's the Spray Lakes Road down south of Canmore. And it's very washboard, very unpleasant to ride on. I was down there hiking over the summer and it hasn't gotten any better. So I'm not surprised that was the road that happened on, because there's a lot of bouncing that happens. Again, not a great road to drive down. But you brought up a point that I was actually going to bring up, which is, so in Alberta, we change our tires for summer and winter. Most people do, just because the winter conditions are so challenging that it's nice to have winter tires. But when you put new tires on, you torque your wheels. And even if you didn't change your tires, you still should be torquing your wheels on your car at least once a year, if not every 6 months. And so I find it a bit interesting that that's not a requirement on this wind turbine, because you'd think, I would have expected that they would retorque those bolts every inspection as part of the inspection process. That seems pretty straightforward, considering it is something that's spinning around continuously and exposed to all of these different elements. I don't know if this was just a flaw on this one wind turbine where they didn't check the torque, and maybe it was just something that got missed, and it could be as simple as it not getting onto the inspection report, and so then it wasn't something that was flagged to the inspector every time they were there to check and do that work.
It could be that they're not accessible either. Like I forget what it looks like on the inside of the hub and how those things are connected. And I don't remember if the bolts are inside of the hub where it would be accessible, or if it's on the outside, like you'd have to climb out of the cabin to torque those. I don't remember. Yeah.
That's a great point, because this is something I have to think about a lot in mechanical design, is if something's not accessible, no one's going to maintain it or change it or fix it.
Yeah, not to excuse the maintenance people from something that maybe should have been done, but yeah, it's easy to overlook if you don't see those bolts when you're up there.
Yeah, great point.
And just a note that hand tight is not the same as torque to spec.
Yeah, sometimes hand tightening can be over torque and you can crack it. Sometimes, a lot more often, it's under tightened when you're not torquing it, but a lot of bolts are designed to be tightened to a specific amount, and using a torque wrench will get you dialed into that exact amount, give or take a little bit.
Yeah, if you have a low grade bolt, it's like you say, it's very easy to over torque. Something that's low grade.
Yeah, we've come across that in piping. Some of the couplings have to be, so there's two pieces that clamp around the pipe, and then that where they connect together. There's a hinge on one side and then there's a bolt on the other. And I've definitely had arguments with some installers about how those get tightened, and because some manufacturers require them to be torqued. And so I say, I need to see that you've done that. And they're like, we don't torque these. And I'm like, no, you have to. The installation instructions say they have to be torqued. So you have to do that. If you don't want to torque them, you have to use one of the other ones that doesn't require torquing. And then they don't like that conversation. It's not to be fair, it's not my favorite conversation either. There's usually hundreds of these throughout the site. Some of them are accessible. Unfortunately, some of them aren't. And then there's just me like, no, you got to go torque all of those.
We really enjoyed our conversations and side tangents with Leanne, so we didn't want to edit those out, which means this is a really long episode. So what we're going to do is we're going to take a slight pause here and bring you the second half of the wind turbine failures in our next episode. Sorry for the disappointment. So there you have it. The most common cause of wind turbine failures is blade failures. We also talked about optimizing wind farms and how wind energy has impacted Alberta and also Germany.
And don't forget about that train tangent. Man, I really love trains. They're so great. My favorite form of transportation. Twinkle Toes over there, could you be still, please? For photos, sources, and an episode summary from this week's episode, head to failurology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failurology so more people can find us. If you want to chat with us, our Twitter handle is @Failurology. You can email us at thefailurologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us on our Patreon page. And just so you know, if you reach out to us, we will reply. I'm in charge of that part of the process, and I can guarantee I will respond. Check out the show notes for links to all of these ways to get in touch with us. Thanks everyone for listening, and tune into the next episode, the second part of this wind turbine failure series, where we'll examine generator, gearbox, and foundation failures and share more wind turbine failure examples. Bye everyone. Talk soon.